Alrighty, we're ready to start Unit 7 of 9 in AP Chemistry, and that would be the unit of equilibrium. So just some key things to get started with here. We're going to break this lecture here. It has three big ideas in it, 7.1, 7.2, and 7.3, but this one lecture we're going to break into 2 parts and 2 days. All right, so you'll have enough after today to understand what establishing equilibrium does, and we are going to know what Kc is, and you'll know what those 3 are on the second day. So that'll either be Tuesday, Wednesday, or Wednesday, Thursday, and ultimately, since we have a test here, you have flexibility on when you finish these problems. But after today's lecture, you should be able to do the first 3 problems, of which we are not going to be posting the answers. So this is an assessment, meaning it's more points value, and I'm not going to be posting the key. So, and we're going to add one other thing. You are going to have the question and the answer. I want some more complete things for you to have as a tool when you're doing these. And then when I hand them back with some feedback on them, you'll know what the question was and the answer. It'll just be more useful for you down the stretch as we're heading to that. So, and in turn, I'm giving you a little bit more time to do it. You'll have the weekend to finish that up. But remember, question and answer for all of the problems. And you can do the first 3 after this lecture. All right, so enough about that. Let's start talking about this equilibrium constant. Well, the whole idea behind it is that many reactions are reversible. And you know a lot of these. For instance, water can go from a liquid to a gas. That could be boiling or evaporating. And it can go from a gas to a liquid as condensation. Dissolving of salt. Sure, you can take a salt and you can dissolve it in water, and then you could let that water evaporate, and you would have this second reaction. So in essence, the forward and reverse reaction of each of these is possible. Another good example of this is if you have these gas molecules, and you could think of this as, let's go with oxygen. So there's little O2 molecules, and some of them are actually in the water. That's how fish breathe, obviously. So there's oxygen in there, and depending on the temperature, you can get certain amounts of water if those water molecules have enough energy. So they act in a similar method to the way that ions stay dissolved. So, there's a certain number of oxygen molecules will be in the liquid, and some will be up here as O2 gas molecules. Now, if you increase the pressure on the system, many of those gas molecules will then be, in essence, kind of forced into being into the liquid. So this, notice the size of the gas chamber, volume changed considerably, and the water, of course, is not affected by a change in pressure. So the concentration, that's what those square brackets mean, of A in the water is a lot higher. So we talk about this as this pressure increases, this system here moved to the right, didn't it? Because it became more aqueous. And if you were to back this piston off and lower the pressure, less pressure, then it would shift back to the left, wouldn't it? And there'd be more gas molecules. So that's what we talk about, and it's dependent on the conditions. The conditions can change where that equilibrium lies. And several of you had good question on our kinetics unit, where you're talking about shifting equilibrium, and you weren't quite ready, or actually it was in the last unit they talked about shifting equilibrium in one of the assignments. So that's what that means, and this is a really good graphic to get that idea of how it can move back and forth. It's the same exact reaction. This one is lots of gas, and then you put more pressure on it, and it's lots of aqueous form, so it's shifted to the right. So this is an important slide. This is one you might understand a little better, is your soda pop. I don't know what pop is. Oh, wait, yeah, we're from Minnesota. We call it. Isn't that cool? Canadians obviously call it pop, too. So maybe it's because they're so close to Minnesota. Absorption. You got to watch the spelling of that. We're going to talk about adsorption and some of these different things. But this is absorption of CO2 occurs because when you bubble CO2 through water, you can actually do this with a straw and just blow into the straw. You can change the pH of a solution because the CO2 that you're breathing out will react with the water and make carbonic acid. Now, carbonic acid is going to dissociate, and you know it's not going to dissociate completely because it's not a strong acid. So then it ends up becoming these constituent ions. So like all acids, it will one of the hydrogens break off, part of the definition of it, and you'll have these two ions. So that's how they put that under there, and then by keeping the pressure and a low temperature, you can keep this in such a way so that there's lots of CO2. Now, if you were to, so in other words, it sort of drives this reaction to the left by keeping the pressure and keeping your pop cold. Now, desorption, there's another word, two key vocab words here for you today. Desorption of CO2 occurs when that pressure is alleviated, when it's warmed up, and out come those bubbles, and you can even see it happen. And the way that happens is you start with the products over here, and now they become reactants, and the two ions combine to form an aqueous acid, and that aqueous acid can actually decompose. It's a two-step process there, and then you CO2 and H2O, and out comes the gaseous CO2, and that creates sort of a neat sensation when you're drinking it. Okay. Biology. Hemoglobin combined with oxygen in something called the ravioli of the lungs. It's a Italian pasta that's found in the alveoli. I'm not a biology guy. The alveoli, little air sacs in your lung. Okay, so you breathe in that nice oxygen, and one hemoglobin molecule has these one part of it. If you're talking about one simple molecule, is actually made up of 4 separate proteins. Each of those proteins has a little prosthetic group that sticks out and can grab onto oxygens. And you can see 4 oxygens, 4 O2 atoms, and they're intact as oxygens. It actually it's the iron part of blood. You need iron in your blood, and that part of hemoglobin will grab on. So here comes a little gaseous oxygen, and then whap, it just grabs it, and it can take one hemoglobin molecule, can take 4 of them, and then passes out to let's say you're writing some AP lab report, and your hands cramping up, and your body says, we need more oxygen to write this stupid lab report, and it sends that blood out there, and when there is a lack of oxygen, good old-fashioned diffusion will drive these oxygens to leave the hemoglobin and then go and bond to the tissues that need them and complete that metabolic process of writing your lab report. Okay, so this is a reversible process, obviously, and that's important, right? You got to take the oxygen in, it's got to carry it, and then it's got to let it go, and then it comes back and it gets more oxygen, and it keeps going back and forth. All right, the lead battery in your car. This is important. So one of the things AP is mentioning is they want you to be able to actually explain some of these processes with equilibrium. So this is a new thing, and that's why we're not jumping right into doing the equilibrium calculations. That'll be on the next video. There'll be a little shorter video. This is for today's lecture. You'll have 2 videos. So the lead in a lead battery, and if you've ever carried a battery at the lake or anything, they are very heavy because of that lead that's in there. And they carefully pour a little sulfuric acid in there, and that gets this process started. So what happens is the elemental lead then combines with the sulfate, and you get what is of course going to be a redox reaction, and you will get a loss of electrons over here on the right side, and out comes the electrons, and it makes a nice flow. Now what was really nice about a car battery, it is very easily recharged, and that is where equilibrium comes in. So this is another example you can kind of hammer into your head here a little bit. So this reaction, you can take the electricity. That's what a generator in the car does. Your alternator keeps that electricity coming back to the battery. You know, you need to have that recharging the battery, and as it's spinning, it creates its own electric current, and you just use the momentum of the car to spin it, and it creates its own electric current, which can reverse the process, turn it back into lead and lead oxide, and guess what? Sulfuric acid, and then it'll go back up here, and it will make more electricity. So it's this reversible process, and that's how you keep that battery charged. Now, the battery is used for a lot of things, and it's very important that it has a good fresh charge, especially on these below 0 days. You go out there and it just doesn't want to work very well. Okay, so those are reversible reactions. What we just finished with acids, that's a really good example too. Here's acetic acid, a nice weak acid, vinegar, a little something you put on your salad there, and it breaks up into its ions. Well, this is a reversible process. So this is where they go, you know, all these reactions we've talked up to this point, they don't usually say it's this reaction and it's that reaction. They write one, and usually the desired product is written over on the right. In this case, maybe you're trying to get this hydronium ions. But you can write them either way, and then you use this double arrow, okay? This is at the core. This is a great thing to end the first video here today on, is that double arrow, because that, ladies and gentlemen, is equilibrium, and it's going forward and it's going backwards. And we're going to talk a little bit more about the process of this when we do the next lecture. But we're at 14 minutes, so I will stop here, and you can watch immediately lecture 2, and I'll go to the next slide.